all these little exercises here actually point to some things that we should keep in mind as we are doing these problems. And that's first, if the electric field and the path vector are in the same direction, then what did we get for delta V? What sign was it? It was negative, wasn't it? Because we said that the electric field was pointing down, and the path was pointing down. Okay. The dot product E dot dl, if they're in the same direction, will give you positive, but you're multiplying by a negative sign. There's always this negative sign out front. So delta V is less than 0. Okay. If the electric field and delta L are in opposite directions, then delta V was, what do we get there? Positive. Okay, it was something greater than 0. If the electric field and delta L are perpendicular, then delta V was 0. Delta V was equal to 0. Okay? So it's very easy to get the signs confused when you're doing the calculations. If you keep these rules in mind, it can help you check your work. Okay? Now, what is the significance of this? Well, again, think back to what the definition is, which we're talking about potential energy per unit charge. If you have an electric field, let's think about a positive charge, for example. If I had a positive charge that moved along this path and the electric field was in that direction, what would happen to the kinetic energy of the system? What would happen to the kinetic energy of the proton? It would increase, right? So delta K would be greater than 0, but the potential energy of the system would decrease, right? It would go down. So delta U would be less than 0. Well, if I take this delta U and divide it by a positive charge, then that gives me delta V. That should also be less than 0, negative, right? So if you can think about the delta V as giving you what happens to the potential energy in the case of a positive charge moving along that path. Okay, again, there doesn't necessarily have to be a charge moving there, but you can use the positive charge as a test case to think about the energy. The change in the potential energy for the case of a positive charge has got to be the same as the change in electric potential. Okay, and then in this, like as we saw in this last case, what if we don't have a situation where the field is parallel, anti-parallel, or perpendicular? If the field was like this and the path was down, well, you can still check the direction because you can always break up the field into components. You can say there's a component of the field that's perpendicular to the path, and there's a component of the field that's parallel or anti-parallel, depending on the direction, to the path. The perpendicular component isn't going to contribute to the delta V, right? Because we know that any field direction that's perpendicular to the path gives you a delta V of 0. So the only thing that matters here is what component of the field lies along that path vector. If it's in the same direction as that path vector, you get a positive, or excuse me, you get a negative. If it's in the opposite direction, if you had a field like so, then this delta V would be greater than 0. This delta V would be greater than 0. This delta V would be less than 0. Okay? So there's always sorts of ways to break up the result to check it. And again, also the other way we can think about it is the angle. If that's theta, then we can say delta V is negative E times magnitude of E times the magnitude of delta L times the cosine of the angle between them. Okay. In this case, the cosine is a positive, so you get a negative delta V. In this case, the cosine is a negative, you get a positive delta V. Okay. Questions on this? Let's try one more just to give us a different twist on things. Let's see. We'll skip that one. Probably should. Well, maybe we'll come back to this one later if we have time. We know the potential difference. If we go along a path from B to C, we find that the potential difference is negative 500 volts. What's the magnitude of the electric field? See if you can work it out. You know the position of B, you know the position of C, and you know the potential difference. What's the magnitude of the field? Okay, so 250 volts per meter. We can write actually the sort of opposite relationship here. We can say that if we know the delta V is the dot product, then you can also say that the electric field, at least the magnitude, well, let's write it this way. The electric field is going to be negative of delta V. We should do it this way. If you know the field lies along some direction, then you can find the electric field by taking the potential difference dividing by the path along that direction. Okay, so we're just using the opposite relationship here. We don't care about the sign, so we're just saying that the electric field in this particular case, the magnitude is just delta V over the magnitude of delta L. Okay, so that gives you 500 divided by 2 meters is 250. And note the units here. Because we can do this, we get units of volts per meter. That's exactly equivalent to a unit of a Newton per Coulomb. So we've been writing electric field in units of newtons per Coulomb. Well, we're going to probably start seeing them in volts per meter. It's the exact same thing. 1 volt per meter is 1 Newton per Coulomb. All right, let's go back to this question. One more question. We've got a lot of them today, but this is actually a pretty useful one to do. We now have a path that goes from A to C. A is 320 meters. C is 800 meters. And the electric field has both an X and a Y component. Find delta V along the path from A to C. And this one's kind of useful to do because we can talk about some different ways of doing this. Okay, so most of us are getting positive 200 volts. And so we can go through and do the dot product, and we'll just sketch it out real quick. We have a delta L, which I can say is final minus initial, right? So I have 800 minus 320 meters, final minus initial. And so we have 520 meters. We're taking the dot product of that with negative 200, negative 400, 0. So we say delta V is negative of negative 200 times 5 plus negative 400 times 2. What did I do? Negative 2? Thank you. Because we're going in the downward direction. Times a negative 2, and then plus 0. Okay? So what do we get? We get a negative sign. We get negative 1,000 in here plus positive 800. And so inside the parentheses, I get negative 200, but then I multiply by a negative sign, so I get 200 volts. Okay. Now, it's a little bit difficult to check the result in this particular case because your path is going this way and your field's going that way, and so it's hard to see what components are perpendicular and what components are parallel to that path. We could work this out a different way, though. Do we necessarily have to choose a path that goes directly from A to B or A to C? What other path could we choose? Okay, why don't we go from A to B and then B to C, all right? So we go from A to B. Let me erase some of this here. If I go from A to B, then what's my path vector? X is 5, Y is 0, Z is 0, okay? So I have delta V going from A to B, we have a negative, I have negative 200 times 5, and then 400 times 0 and 0 times 0, so I'm just going to get positive 1,000 volts. But if I go from B to C, what's delta L for that path? What's the x component? 0. Y component is negative 2, 0. Field is the same. So when we go from B to C now, we have negative of, well, is the negative 200 going to contribute at all here? Negative 200 times 0 gives me 0, plus negative 400 times negative 2, plus 0. I get negative 800, right? And then I can just add the two up and say that the total is when I go from A to B and then B to C. Gives me 1,000 minus 800 or plus 200. And you can kind of even see that coming out of the math here. You have 1,000 here and 800 here from just adding those two components together. I haven't proved this. It works out, but I haven't formally proved it. But this is a useful property that's called path independence. Delta V's are independent of path. Independent of path. As long as the initial point and the final point are the same, you can choose any path you want, and you've got to get the same result. Okay, I haven't formally proved that, but it works out that way, and it's a very useful result. Another way we can write this, if I say delta V from A to C. Now, as the delta indicates, it's a subtraction. It's a final minus initial. I can say V sub C minus V sub A. Well, this implies that there is a value for the potential at a location C and a value for the potential at a location A. How we calculate that is a different story, and we'll deal with that later in the next lecture. But there is a particular value at the potential. We're finding the difference between them. So if I add these two pieces together, I can say VB minus VA plus VC minus VB. VB will cancel out. We have positive and negative. And I have VC and a negative VA here, so I get back VC minus VA. Okay, so that tends to suggest that, again, you can do this adding up of the paths and get the same result. Okay. All right.